In August 2004, the Rion Antirion Bridge opened to traffic for the first time. The mighty structure is an engineering masterpiece of the modern age. Spanning almost 3 kilometers across the Gulf of Corinth, this engineering colossus boasts the longest fully suspended deck, the deepest foundations, and the largest supporting piers of any bridge on Earth. For Chief Engineer Panagiotis Papanikolaou, it was a project he had dreamt of for years.
The bridge was something that always excited me, that one day maybe it will happen.
However, a catalogue of natural challenges meant that, for centuries, the idea of bridging this foreboding water had seemed impossible.
We are sitting now from the side of the Peloponnese, and across is the continental Greece. Years ago, those things were very close, and then they drifted apart. There is tectonic faults all along this area, and we are bound by mountains from both sides. And the geometry of these sections makes it a natural wind tunnel.
And there was another earth-shattering challenge.
This particular strait here is the highest seismic zone of Greece and the highest seismic zone of Europe.
It's a long list of seemingly insurmountable engineering problems. The two landmasses either side are constantly drifting apart. There's deep water, high winds, and major earthquake risks, all of which combine to make the building of the Rion Antirion Bridge a huge, apparently unachievable undertaking. But the need for a safe crossing was desperate. The perilous waters of the Gulf of Corinth often made ferry crossings impossible and cut the peninsula off from important services.
There are examples of people that lost their lives because the ferries were not crossing due to bad weather and they could not come to the hospital. There was a need of this bridge.
So, in the 1990s, the government decided to attempt one of the most ambitious engineering feats in modern Greek history. The first seemingly impossible challenge to overcome was the almost 3-kilometer gap between the two shorelines. The vast expanse meant a single-span bridge was out of the question. So any design would require building supporting towers into waters up to 65 meters deep, far deeper than any bridge designer would willingly choose.
The cross-sections below sea level, we go to deep waters from very beginning of the shore. No matter what type of bridge we want to select, we could not escape the depth of water.
In order to overcome this daunting obstacle, Panagiotis and his fellow engineers would need to draw on history's great innovators to make the impossible possible. Building in water has always taxed engineers to the limit. Early lighthouses relied on Mother Nature to provide convenient rock for foundations. Fine for lighthouses, useless for bridge building. Creating artificial islands was time-consuming and impractical in deep water. In the 19th century, pressurized structures called caissons were developed to create underwater building sites, but they were both difficult and dangerous. Fortunately, in the 20th century, a new technique was on the horizon. To build a bridge across the mighty Gulf of Corinth, engineers would need to draw on a radical technique, brilliantly exploited by a bold British engineer nearly 6 decades earlier. Engineering genius Guy Monksul would develop a method in the 1940s that emphatically conquered the challenge of building at sea. Professor Luke Bisbee is heading out far into the English Channel to see the remains of one of the engineering innovators' most audacious and seemingly impossible creations.
Monksul's influence in contemporary engineering, I don't think, really can be overstated. This was really the first time that this had ever been attempted, and so it was really quite a daring feat of engineering.
It was an innovation triggered by the Second World War. At the outbreak of the war, it became clear that the River Thames was a prime target for German bombers, wanting to destroy London's docks and lay mines to disrupt Allied shipping. So civil engineer Guy Monksul suggested a radical new design for offshore sea defences. Naval forts consisting of two 80-foot-high concrete towers, each containing 4 floors of accommodation and topped by a gun deck. However, the ingenious part of Monksul's design was not the layout of the fort, but how they would be constructed and deployed. These forts, like one known as Knock John that Luke is visiting, completely broke the mold.
Knock John here was towed out 3 to 6 miles from where it was constructed on land, and then it was sunk in place, out exactly where you see it.
Monksul's brilliant idea was to design the bases of the forts as huge hollow concrete barges that, despite their enormous weight, had the buoyancy to float.
Monksul built the forts on top of these large concrete barges and then calculated how large the barges needed to be in order to hold the weight of the fort so they could be taken out and then sunk in place.
After being constructed in a dry dock, the massive 4,500-ton concrete forts were towed far out to sea, complete with its 100-man crew already on board.
When they had it in the place where they wanted it, they essentially just pulled out a stopcock at one end and let the water flow in. As the water was flowing in, the barge started to list in the water, and eventually the nose dipped under the water.
Footage from the time shows just how dramatic and seemingly perilous the process was.
All 100 men were hanging on as the fort was sinking at 35 degrees.
Despite its terrifyingly dramatic submersion, Monksul's groundbreaking design worked perfectly.
The bottom of the barge basically filled up with water, and eventually the entire barge sunk to the bottom and flattened out.
In the years ahead, the forts helped British forces shoot down 22 enemy aircraft and 30 flying bombs, not only protecting London from attack, but making engineering history at the same time.
The influence of this type of construction you can see in all different facets of engineering today. You can see it in the offshore oil and gas industry with oil platforms. You can see it being used as foundations for wind turbines. And of course, you can see it being used as a way of placing foundations for large bridge structures around the world.
And the most impressive use of floating concrete is at the Rion Antirion Bridge. Facing the challenge of building 4 enormous concrete bridge supports, Papa Nicholas and his colleagues take the principles so brilliantly exploited by Guy Monksul and supersize them. In 1998, construction begins. Each hollow pier footing is built in dry dock, but on a scale that Guy Monksul could never have imagined. Each one is the size of a football field and weighs an extraordinary 70,000 tons. But before the footings can be moved into position, the engineers face an additional challenge that Monksul didn't have. The Gulf of Corinth lies in one of the most active seismic zones in Europe. In an earthquake, the soft seabed there would liquefy, causing the piers to sink and the bridge to collapse. Unless an answer could be found, the project was destined to fail.
We had to find the solutions how to reinforce the subsoil in order to be able to handle those weights, those big structures, and also to withstand the earthquake.
The engineers come up with a radical solution. They drive hundreds of 30-meter-long tubes deep into the soil in the areas where the 4 piers are to sit.
Imagine the foundation being like a yogurt. It's like having yogurt, and you put stores inside to reinforce them.
This ingenious idea stabilizes the seabed. And where the bridge footings are usually anchored into the ground, here they are placed on a 3-meter-thick layer of gravel, allowing them to move freely in the event of an earthquake.
Very innovative design, first time done in engineering, first time done in this bridge. Without this solution, it would have been impossible to build the bridge.
With the foundations laid, the engineers maneuver the enormous concrete pier bases 1 kilometre out into the Gulf. The engineers then begin one of the most extraordinary and audacious parts of the build. They continue to build up the massive piers while they are still floating.
We are exactly in the area here where this portion that I'm sitting on is the one that was constructed in the dry dock and wet dock. And from here and further up, it was constructed in situ, right here at this location.
Each new layer of heavy concrete sinks the pier further, pushing it down towards the seabed. As building continues, the mega structure finally starts to rise from the waves. The end result is 4 enormous hollow foundation piers, unlike for any previous bridge, creating massive sub-aqua concrete caverns.
We are 64 meters below sea level. This is the footing. The footing has dimensions of around 90 meters in diameter. Just imagine a soccer field.
The Rion Antirion Bridge crossing the Gulf of Corinth in Greece is a modern engineering marvel. 320,000 cubic meters of concrete, more than 100,000 tons of steel, and 62 kilometers of cabling have gone into creating the longest fully suspended cable-stayed bridge on the planet. In attempting a construction of this scale and complexity, Panagiotis Papanikolaou and his fellow engineers had set themselves a seemingly impossible challenge. The Gulf of Corinth is one of the most important and busiest shipping routes in Europe. Even at its narrowest, it's nearly 3 kilometers wide.
Of course, what you try to do is to find the closest possible part of the strait, so to have the smallest possible bridge for economical reasons. But of course, we had to respect the navigation channels.
To find a design capable of spanning this gap without interfering with shipping, the engineers need to turn to the great innovators of the past for inspiration. It was the Romans who first engineered solid bridges that were built to last, using stone and a simple revolutionary shape, the arch. However, the wider the gap, the more arches were needed, and the heavier the bridge became. For hundreds of years, Inca communities in the high Andes crossed gorges using suspended wooden walkways. It's said the 16th century Spanish conquistadors arriving in Peru looked in amazement and fear at the swaying bridges that might break at any moment. What was needed were new building materials and a new approach. And in 1826, one brilliant engineer showed how to do it in style. The Menai suspension bridge is arguably the ultimate achievement of Thomas Telford, one of Britain's finest ever civil engineers.
Telford was an accomplished engineer, of course. At this stage, he had designed canals and roads and bridges. He'd never built anything on this scale before, and so this bridge was to be really his greatest challenge.
The then busy Menai Strait separated mainland Wales from the island of Anglesey. Until then, bridging it would have been impossible. A traditional arch design would not only need to be enormous, but it would seriously impair the passage of tall ships along the waterway.
Imagine this as being the strait here, and these are the valley walls on either side of the strait. Basically, you cut your bits into shape, and you then have to gradually build your arch, adding the bits of the arch as you go. And if you imagine that as now being the completed arch, and we have our load coming along here, you can see that the compression forces that come from that car flow down through the various sections of the arch and into the abutments on either side of the valley.
Now, the problem that Telford faced was that as you're building an arch, you would have to have some supports down here underneath the middle of the arch so that as you're building it, the blocks don't fall into the strait. And that would require some scaffolding. And this was just not acceptable to the Admiralty at the time because this is a very busy shipping channel and they required 100 feet of clearance above the high water mark. And that led Telford to have to consider something that could give him a very long, clear span with no supports in the water, even during construction.
What Telford came up with was the world's first major long-span suspension bridge.
For a suspension bridge, you need two very strong abutments, and then you need two towers. And then what you do is once you've built your towers, you take a cable like these guys, and you string these up and over the towers, and then you drop hanger cables down from the main cables, and then put your bridge deck in place. And then once your bridge is completed, if you have a load that comes along, say our car here, it comes along, and now when the load gets out near the middle of the span, the load from the car then gets transferred up through the hanger cables into the main cable up over the tower. The tension in that cable gets anchored in these strong abutments, and the compression force here goes down into the foundations in the bedrock. That's essentially how a suspension bridge works, like this beautiful bridge we have here.
Telford's suspended deck was a stroke of engineering virtuosity.
The key advantages of a suspension bridge are that you can span long distances with no supports below the bridge deck. So you can get very long, clear, unsupported spans because all of the support is coming from the suspending cables and the main cables up above you. So below the bridge deck, there's absolutely no obstructions, which in a strait is obviously a very important thing.
Clearly, a suspended bridge was the obvious solution for Papa Nicholas and his fellow engineers in the Gulf of Corinth. But they would have to do it on a whole other scale. When completed, the Rion Antirion Bridge would need to be an incredible 7 times longer than the Menai. Unlike the main anchored cables of Telford's suspension bridge, this cable stay design uses individual cables, radiating from 4 huge pylons, spaced just half a kilometre apart. Each cable set holding up a 12-metre-long section of deck. In 2003, the mammoth operation of fitting the deck begins. The sections are floated out into the Gulf of Corinth and attached either side of each pylon until they meet in the middle, an operation that takes more than a year. But this bridge's engineers face another potentially deadly challenge that Thomas Telford didn't have to worry about in Menai. This is one of the most active earthquake zones in Europe.
The wind, it's a phenomenon which is predictable. So you are ready for it. You have designed the bridge to take it. Earthquake is something different.
Expansion joints allow the deck to stretch as the 2 land masses either side gradually drift apart. But protecting it against a massive earthquake will require a groundbreaking new approach.
What you see is a deck just going through the pylons, does not touch, does not sit on the pylons. This one has this unique feature of the full suspension deck.
Instead of resting on each pier, the deck hangs just above, creating one huge 2.3 kilometre long, fully suspended floating deck. If any earthquake strikes, flexibility is key. The piers can move on their foundations, and if the deck was attached when this happened, it could buckle and break. But it's also important that the deck doesn't sway during the regular high winds experienced in the Gulf. The problem the engineers face is how to ensure rigidity in normal conditions, but allow flexibility during earthquakes. The solution? The world's biggest shock absorbers.
They are similar with the shock absorbers that we have in the cars. They allow some movement, but what they do mostly, they absorb this energy.
If severe movement occurs, a simple fuse breaks and brings the massive dampers into play.
The moment that the fuse breaks, the small tube can get inside the large tube. At that point, the dampers come into action. This device does not work for years. And then one day, you want it to work. and everything has to be perfect. So if it was something too sophisticated, usually the moment you want them to work, they don't work.
This quake-busting design proved its worth 4 years after the bridge opened. When a 6.4 scale earthquake hit the Rion Antirion in 2008, the innovative damping system kicked into action, saving the bridge from almost certain disaster. Engineers of the almost 3-kilometre-long Rion Antirion Bridge faced huge environmental and geological challenges. In one of the most seismically active regions in Europe, cutting-edge technology safeguards the bridge from earthquakes. But the Rion Antirion's designers and engineers face another massive environmental challenge.
We are like inside the wind channel here, so there is always wind. Thing is that as you go higher and higher from the sea level, the wind is getting higher and higher, the wind speed.
To protect the massive structure, engineers will need to take a lesson from history. When the Tacoma Narrow Suspension Bridge opened near Seattle, USA in July 1940, it was thought to be at the forefront of bridge design. But very quickly it became clear there was a problem, and it led to it being nicknamed Galloping Gertie. Just 4 months after its opening, despite a relatively low 40-mile-per-hour wind, the bridge's twisting motion became so violent that the bridge deck suffered a catastrophic failure and crashed almost 200 feet into the waters below. An inquiry found the wind was hitting the solid edges of the deck, creating an unstable oscillation that fed off itself, amplifying to the point of disaster. In the Greek Gulf of Corinth, the wind conditions are far more severe than for the Tacoma Narrows Bridge. The mountainous landscape creates a funnel where winds of 70 miles per hour are not uncommon. The aerodynamics of the bridge deck are crucial.
One of the solutions is to put fairings, spoilers. The same thing on a fast car, you have the spoilers underneath, just to improve the aerodynamic shape of the fast car that drives through the wind. Here is the wind drives through the bridge.
These fairings safeguard the deck from gusts of over 150 miles per hour. But the massive cables holding it up also need to be strong enough to survive this extreme environment. The designers of the Greek bridge will need to draw on an innovation from history that conquered a challenge similarly once thought impossible. In the second half of the 19th century, the growing metropolis of New York was being stunted by the wide waterway of the East River. Until then, the only way for people and goods to cross from Brooklyn to Manhattan was by ferry.
You see here Manhattan to my left and Brooklyn to my right. At the time, you could imagine just a river teeming with boats.
But in 1867, traffic suddenly ground to a halt.
A cold spell actually froze the East River over and essentially halted commerce because you could walk across the East River at the time on the ice, but you couldn't actually trade. So it was at that point when voices really kind of mounted, demanding a permanent kind of structural connection between the two cities with a bridge to have this lasting connection so that you could have reliable transportation and trade.
The man given the job was German-born engineer John Augustus Rübling, and what he designed still inspires fellow engineers today.
Just the concept of actually spanning over such a long distance at such a height was earth-shattering. No bridge had been built even close to this span.
The Brooklyn Bridge, completed in 1883 and spanning over 1,800 meters, was made possible by Rübling's revolutionary use of a new material, steel.
Just thinking of actually building a bridge, not of masonry as you would find in kind of traditional European style, but saying we have this new material, steel, we'll build it, the entire deck and the cables of steel. This is an absolute engineering marvel.
Steel was stronger, lighter, and more flexible than iron. But Roebling decided to exploit its properties even further in the bridge's 4 mighty suspension cables. By bundling together hundreds of parallel steel wires to create super strength and super safe cables. At Columbia University's Engineering Testing Lab, engineer Adrian Brugger can demonstrate just how much safer this technology is.
This cable is made up of actually independent, small 5mm circular wires. In this case, there's 9,000 wires. Those wires are then grouped into what we call strands. You actually take those and you compact those into the cable. This is a kind of a huge leap from the technology we had before, because before what we had was more or less serialized systems, such as chains or these large I-bars, where if one of these I-bars failed, generally that meant that the entire bridge failed. If one of these wires happens to be bad or has a crack in it, then the entire cable still has 8,999 other intact wires.
To compare the system used on the Brooklyn Bridge with what came before, Adrian will use the university's giant universal tester.
And more or less, a universal testing machine just means that it's a machine that is built to crush things and rip them apart.
First to be tested will be a solid steel bar.
This will be very similar to what you would have on an old bridge, pre-Brooklyn Bridge, for example.
The steel bar has been weakened at a specific point and will be stretched under massive tension to simulate a fail on a bridge.
So we expect this bar to fail at around a good 200 tons. Right now you can see the necking is starting at about a quarter up from the reduced sections, exactly where we wanted it, and it'll become more and more pronounced kind of as we see it now. The energy release was massive, and now the specimen is just catastrophically failed. It's broken.
Such an explosive failure could result in the collapse of a whole bridge, as tragically happened with Silver Bridge in Ohio, causing the loss of dozens of lives. Next, a multi-stranded steel cable is locked into place. This time, as it is stretched, it's subjected to extreme heat to weaken it and simulate a fail.
So we are seeing this cascading failure right now. You can see each wire is actually breaking one after another. It's not just this one catastrophic failure, but rather this cascade.
Unlike the sudden failure of the bar, when the cable starts to fail, the remaining wires take up the load. And even if all the wires were to fail, the energy released is gradual rather than one huge explosion.
So what you saw there was, exactly why suspension bridge wires are such a great solution. But you can see that you didn't have this one catastrophic explosion and just failure of the member, but rather each one of these wires actually broke.
This steel technology enabled John Roebling to design what was then the world's longest and strongest bridge, and an iconic engineering masterpiece.
This bridge would eclipse every other structure in the entire America. So it would be the tallest structure anywhere. So just a person actually standing on the tower would be on essentially the first skyscraper in the United States.
"55 meters above the Gulf of Corinth. Similar technology to that used in Roebling's historic Brooklyn Bridge keeps the ultra-modern Rion Antirion Bridge from crashing into the water.
Every cable is made by individual strands. They are parallel. Each strand is 50 millimeters diameter, more or less. Each strand carries more or less the same load. The only thing we do as the cable gets bigger and bigger, we put more and more strands, from 37 strands in the small cables up to 73 strands in the longest cable.
But here, the strong winds mean the cables themselves need extra protection. At a wind tunnel facility, Professor Luke Bisbee is about to see just how destructive wind can be.
All right, so we're going to start it up and we'll see what happens. If this were the cable in a real bridge, this type of oscillation would be very worrying to the designers. Because what this would mean is that the metal that forms the cable would be being stressed repeatedly back and forth, and eventually in a metal cable that can lead to fatigue, which can cause cracking, and hence potentially failure of the structure. So the structure could collapse due to oscillations such as this.
When the wind strikes a cylindrical structure like a cable, it separates, then rejoins on the other side, causing the structure to oscillate, a hazardous phenomenon known as vortex shedding. Over the years, this dramatic effect has caused the collapse of several large cylindrical structures, such as chimneys and towers. In 1957, pioneering British scientist Christopher Kit Scruton realized that adding a simple fin to cylindrical structures would break up the wind vortices and reduce the vibrations that could lead to failure. He called it the helical strake.
Just seeing a little bit of vibration here, not too much. This is really incredible that this simple spiral can completely prevent the motion of this simulated bridge cable. With the helical strake, we get this disruption of the flow pattern, we introduce some turbulence, and both the formation of the vortices and the vibration of the cable both stop. The helical strake seems to be working. Since Kit Scruton invented the helical strake back in the 50s and 60s, it's been applied to tens of thousands of structures and chimneys and bridges around the world, and has really saved them from potential catastrophic collapse due to wind effects.
Scruton's helical strakes are integrated into every single one of the 62 kilometers worth of cabling on the Rion Antirion Bridge. These, combined with the spoiler-like deck fairings, make this bridge as windproof as any on Earth. The stunning Rion Antirion Bridge in Greece is one of the wonders of the engineering world. Built in one of Europe's most active seismic zones, its designers have not only had to engineer it to repel earthquakes and high winds, but also build it in deep water on substandard soil. The underwater construction may be an enormous mass of heavy concrete, but above water, the designers needed to create an elegant bridge that added to the landscape around it rather than scarring it. And to do so would require combining strength and beauty in an extremely hostile environment.
The pylon are the elements that at the end of the day will take most of the part of the earthquake. It is the pylon responsibility to take those loads down to the foundations.
It's a challenge that may have been impossible without one of the great engineering innovators of the past. In 1928, renowned Swiss civil engineer Robert Maillard won a competition to design a bridge linking two remote towns, 90 meters above the steep Salgina Valley. The result was the Salgina-Tobel Bridge. Designated an international engineering landmark, Maillard's bridge proved to the world that concrete could be both practical and beautiful. Engineer Urs Meier has been a lifelong fan of the iconic structure, but for the first time is about to see it from an entirely new perspective.
Up to now, I have seen the bridge from the deck, from the side, admiring the bridge. And now I have the chance to see the arch very close. I'm very, very happy. From here, I really can appreciate the structure. From this location, we have a very nice close-up. Nobody else can have. Mayer was a master in designing such slender elements like columns, like arches. It's a dream, this position. I never realized that it's so beautiful, so slender. Must have been fascinating, dramatical to build such a bridge above this gorge. Mayer was the very first who realized the potential of steel-reinforced concrete. And this here is his masterpiece.
Building a bridge in this remote part of eastern Switzerland required great ingenuity.
We live here in a wonderful environment, but more often there is storm here, there is snow, there are avalanches, there are landslides, and Mayer had to face all these dramatical challenges to construct this bridge.
Concrete is strong in compression, but reinforcing it with steel bars also gives it strength in tension and allows it to be manipulated into almost any shape. Mayer designed an elegant three-pinned hollow box arch supported by reinforced concrete columns. This made it strong enough to transmit the bridge loads to the foundations, but with the flexibility to absorb any ground movements that could cause dangerous cracks to form. And Mayer's sleek design used less reinforced concrete, making it cheaper to build. But some were still skeptical.
At that time, there were no similar bridges of this size. People did not believe that this would work. But Mayer had already such an excellent name, not only in Switzerland, also abroad, that they trusted him and said, OK, go ahead.
When it opened in August 1930, the Salgino-Tobel Bridge was hailed an engineering and artistic triumph, showing concrete bridges could be both functional and beautiful.
Concrete is often having a bad name, and people think it's an ugly material, ugly application. And this application here proves that this has not to be the case. Mayer proved that design of a bridge is art.
A 1,000 miles away in Greece, Mayer's influence can be seen at the Rion Antirion Bridge. The pier heads consist of 4 slender reinforced concrete pylons that combine cost-saving minimalism, flexible strength, and elegant design.
So from the bottom, it's huge, and as we go towards the top, we try to make it more elegant for aesthetic point of view, but also for saving of material and for saving of mass. At different locations of the bridge, you'll find different types and different qualities of concrete. The higher the quality, the more expensive it is.
Its 780,000 tons of uniquely engineered reinforced concrete ensure this bridge could survive an earthquake of 7 on the Richter scale.
You start the 4 pylons that you see, and then they connect at the top to the pylon head, a very critical element that takes the loads carried by the cables to the top.
The Rion Antirion Bridge has not only redrawn the map of Greece, it has rewritten the rules of bridge engineering forever, and stands as a testament to the people past and present who designed and built it.
Floating a huge structure of 80,000 tons for months and keep building it in floating positions, or transporting this structure or putting at the right location, meeting the last piece of the deck or the doping span, these things look impossible. And then as long as you keep working, get closer and closer, then you see you can be close to the millimeter and they fit together.
By drawing on the innovations of the past, adapting, improving, and making groundbreaking innovations of their own, the engineers and designers of this incredible bridge have succeeded in making the impossible possible.
Myself, I'm coming from the north part, and I experienced many times while I was traveling as a student, having to go all around, to go to Athens, see the bridge, employs around 100 people. It fills me with pride because for me, we are a big family and we all work together. That's how I feel.